IPv4, the initial version of the Internet Protocol, came into use as a standalone specification, serving as a key element in Internet networking since its introduction on SATNet in 1982 and the ARPANET in January 1983. Despite being succeeded by IPv6, IPv4 remains predominantly utilized for routing Internet traffic today. With a 32-bit address space allowing for 4,194,090,7,296 unique addresses, IPv4 faces challenges due to the escalating demands of the global Internet, leading to the issue of IPv4 address exhaustion during the transitioning phase to IPv6. The Internet Protocol bestows Internet working capabilities at the Internet layer, offering a universal addressing system, enabling the transmission of data packets efficiently. Operating on a best effort delivery model, IPv4 does not assure delivery or sequence integrity. These aspects can be managed by higher layer protocols like the Transmission Control Protocol, TCP. Through continuous advancements, the history of TCP/IP evolved from previous combined specifications to distinct protocols, emphasizing the significance of IPv4 showcased in IETF publication RFC 791. IPv4 allocation strategies initially divided IP addresses into network identifiers and host identifiers. Over time, evolving from classful networking towards classless interdomain routing, CIDR, and variable length subnet masks, VLSM, present-day deployment offers more flexibility in address management. With private address allocations, multicast segments, and reserved address spaces, the system can cater to specific networking requirements effectively. Reserved address blocks and subnetting principles in IPv4 intrinsically manage the distribution of addresses while maintaining network integrity. Private networks utilize designated address ranges, enhancing security and ensuring efficient data transmission within confined environments. In contrast, link local addressing aims to facilitate auto-configuration procedures when formal IP address assignments are not feasible. Encouraging efficient address allocation, IPv4 continues to serve as a foundational element in today's Internet landscape, adapting to evolving networking demands and setting the stage for the global transition towards the enhanced capabilities of IPv6. An IP packet comprises a header section and a data section, lacking data checksums or any footer beyond the data part. Typically, IP packets are encapsulated in frames by the link layer, which appends a CRC footer to detect most errors. Alongside this, many transport layer protocols carried by IP implement their own error-checking mechanisms. The IPv4 packet header encompasses 14 fields, with 13 of them being obligatory, and the 14th one, aptly named options, being optional. The fields within the header are organized with the most significant byte first, known as network byte order. The version field, the foremost header field in an IP packet, always holds the value 4 for IPv4. The Internet Header Length, IHL field, indicates the size of the IPv4 header by specifying the number of 32-bit words within the header. The Differentiated Services Code Point, DSCP field, originally designated as the Type of Service, TOS, now stands for Differentiated Services and is particularly useful for real-time data streaming applications like Voice over IP. Explicit Congestion Notification, ECN, allows for end-to-end notification of network congestion without packet drops in supported environments. The total length field defines the total packet size in bytes, including the header and data, with a range from 20 to 65,535 bytes. The identification field serves to uniquely identify fragments of a single IP datagram. It is important for the flags field to indicate whether a datagram can be fragmented, thus affecting packet routing. The fragment offset field specifies the offset of a fragment relative to the original unfragmented IP datagram, crucial for reassembly at the receiving end. Time to live, TTL, sets a limit on a datagram's lifetime to prevent network failures caused by routing loops. The protocol field defines the transport layer protocol used in the data section of the IP datagram, based on a list of IP protocol numbers maintained by IANA. The header checksum field is utilized for error checking of the header. The source address field contains the sender's IPv4 address, which might be altered in transit by network address translation. The destination address field holds the intended recipient's IPv4 address, which could also be subject to modification by NAT. The options field, rarely used, requires additional 32-bit words in multiples to hold all options, often raising security concerns that can lead to packet blocks by some routers. IP fragmentation allows for the transmission of datagrams between networks of varying MTU sizes, involving fragmentation at routers in IPv4 and path MTU discovery in IPv6. When fragments are refragmented, the identification field remains constant, aiding in reassembly at the recipient by recognizing fragments from the same original datagram. Assistive protocols like ARP and DHCP facilitate the association between hardware and IP addresses, ensuring the accurate delivery of IP packets across networks.